In this lesson, we're going to talk about problem solving. So to get you started, what I want to look at is just a few questions for you to think about. Now, this is sort of an illustration of problem solving in its own right. So let's try to go one at a time, and feel free to pause the video if at any point you think you know some sort of answer, or maybe you need to pause and try something different. We'll see. So first off, how long was the 100 Years' War? Well, if this were more interactive, we could talk about what you probably think it is. It's probably, well, it was 100 years, right? Well, it was actually 116 years. Sorry, no good. Which country makes Panama hats? Well, you might think about it for a second and say, well, it's probably Panama. Nope, it's Ecuador. In what month do the Russians celebrate the October Revolution? Okay, well, maybe October, or maybe at this point you're thinking, should I look at this another way? Maybe you're thinking, oh, maybe it was October, November, September. Somewhere in there, these answers seem to be a little funny. And you would be right. Back in a different calendar, they actually had it in November where they're celebrating the Russians' October Revolution. So now I open a question to you. It would be wise to try to figure out a way to get these answers right. You probably would just keep guessing and guessing and playing around with this and saying, okay, it's probably the obvious answer being wrong, but I don't know how to get it any other way. Sure you do. You have technology at your fingertips like you've never had before. So I ask you the question, and I want you to get the right answer. From which animals do we get catgut? Pause if you need to. Figure out the right answer. What it boils down to is the right answer could be found on the internet or something. Figure it out. What animal do we get catgut from? Alright, assuming you have checked that out, I'll go ahead and show you the answer. Maybe you found it. Sheep and horses. Alright. The Canary Islands in the Pacific are named after what animal? Figure out what the answer is. It's actually dogs. And if you think about canine, you can kind of see where maybe there's a relationship here. All right, last one. Again, feel free to pause to get the answer. What is a camel's hairbrush made of? Squirrel fur. What's the moral of the story here? If you would have just kept trying to guess based on what's obvious, you would have gotten every question wrong. And in courses, any course that you're taking, it matters that you get the right answer. So finding a way to get the right answer is a good thing to be thinking about. Now in this class, the answers are not just, hey, find it on the internet. You actually want to learn, but this is an illustration of the problem-solving process. At first, we just took a random guess based on the wording of the question. By around question 3, we started thinking, hey, I need to think outside the box because I'm getting it wrong. And then by question 4, I encouraged you to use the tools at your disposal to find out what is the actual answer. And hopefully you got it yourself for the last 3 by simply pausing and looking it up. This is the idea. Our original approach didn't work. We had to change our approach, which turned into look on the internet and see what we find. It's not so much that you're going to succeed or not succeed based on what you know or don't know. It's simply your ability to try. Try your best. Keep working. Keep trying. Never give up. And always work towards the goal that you're seeking. This is how you will succeed. If you give up, there is no chance of success. Let's talk about the problem-solving process. A lot of what we're going to be doing in this course is the problem-solving methods that were originally attributed to polio, although they've been around a lot longer. We need to think about word problems in general for this. You might hear somebody say, I can do math, but I just can't do these word problems. And so people are afraid of word problems. Why are people so afraid of word problems? The idea of mathematics is not so much I can solve a problem, because all that is mimicking somebody. You've seen somebody solve a problem this way, you solve it the same way. But mathematics is more than that. Mathematics is learning to solve problems by thinking about them. And you learn more and more about how to solve particular types of problems so that you can solve new ones too. So let's talk about the methods for a moment. The 4-step process is, first off, you need to understand the problem. Make sure that everything that is said makes sense. And we'll talk about how that fits. And then you want to devise a plan. So this means that you could draw a picture, you could write an equation, you could look for patterns, and I'll show you some interesting things with patterns. Sometimes a guess and check strategy is good enough to get here. Any of these methods are good methods, and we'll talk about them as we go through it. And then once you've made a plan, you want to carry out your plan. Follow your strategy, check each step as you go, and get to a solution. If for some reason you fail, go back to step B. Try a new plan. Try something different. But then you have an answer to the problem after step C. But that's not necessarily good enough. You also want to try to become a better problem solver as you solve problems. Don't just try to get an answer. Think outside the box. So with that said, if there was another way to solve the problem, maybe you could figure it out now that you know an answer. Maybe you could find different strategies to solve the problem. And so you might think about, what could I have done differently to get this problem faster? You might check your answer. You might think of other problems that might use a similar approach. And generally doing this helps you become a better problem solver. If your only goal is to get the answer to one question, you really won't have very good success at problem solving. But if you're really trying and you're really aiming to do your best at becoming a good problem solver, you will find that it works well just to keep thinking in this look back step. So here's your first example that we're going to take a look at. You've got Melissa that lives at the YWCA here at this point A, and she works at Macy's at point B. Now, Melissa usually walks to work, and we want to figure out how many routes could she take to get from her home to work. Do we understand the problem? Probably, but when I say different routes, there's a problem if you don't think about it. A route needs to be efficient in some form. So with that said, if I were to go right and then down and then right, if I were to go back up, that would be inefficient. I kind of took a long route. And so this is one thing we need to define is, what is a route? So let's just add to understanding the problem, routes are efficient. And what that means would be no upward or leftward movements take place. Let's try to work on this problem. Here's a simplified drawing to get from point A to point B. And we want to look for patterns in this drawing. Let's try some simple versions first. Let's just look at a small little piece of the picture. I'm wanting to get from point A to right here. And I want to figure out how many routes are there. Well, I think you could trace them out if you're careful. You could go down and then right twice, or you could go right and then down and then right, or you could go right twice and then down. There are 3 routes in order to do this. All right, let's try another one. Now for this one, you could go down and then 3 rights, or you could go right, down, and 2 rights, or right, right, down, right, or all 3 rights and then down. You'll notice in this case, I get 4 routes. And with 4 routes, we might see a pattern here. Basically, if you look at how many times you can go to the right, the number of routes will just be 1 more than that. I'm going to mark some things on this graph. We established that it would take 3 possible routes to get to here. And it could take 4 possible routes to get to here. You might not be surprised that this number would be a 2. And just by doing a quick flip, this number would be a 3 and a 4. It's the same picture, just flipped vertically instead of horizontally. Now let's also answer some kind of basic questions. There is one way to go to the right once. There's one way to go to the right twice. There's one way to go to the right 3 times. And similarly, there's only one way to go if you have to go straight in one direction. You just go straight in that direction. Any other route would be a waste of time. Now, here's the kind of hard part. How many routes when I look at this spot? You maybe could try to trace them all out. Now, here's the way to think about it. At any point on the grid, if you were to get to this point, you would have gotten there by either a downward movement, starting from here, or a rightward movement starting from here. So with that said, if you want to know the number of routes to get to any given point, you can take the number of routes that would have come just to the left of it, plus the number of routes that would have come just above it, and that'll tell you how many routes you have total. The 3 to the left and the 3 above make 6 routes to get to here. Let me write that down. The number of routes to a given point is the sum of the number of routes to the left and the number of routes above. Let's just use that same principle. To get to this point, there are 6 routes to the left and 4 routes above. That gives me 10 routes, 6 plus 4. Right here, there's 4 routes to the left and 6 routes above. So again, 4 plus 6 is 10. And then finally, for this point, there's 10 routes to the left and 10 routes above. That gives me my final answer that there are actually 20 routes in order to get from point A to point B on this map. If this confused you at all, feel free to go back and take a look at what we just did. See if it makes sense the second time. The idea is every time you can simply add the number to the left and the number above to get your current number. And notice this works with what we did before. 1 plus 1 would give me the 2. 2 plus 1 would give me the 3, and so on. This works every single time. You might have heard of something called Pascal's Triangle. Pascal's Triangle looks like this. If you want to draw Pascal's Triangle, you start with a 1, and then you have 2 1s, and then you start adding as you go down. You put a 1 to the left, you put a 1 to the right, and then you add the 2 numbers directly above to get the next one. So you'll notice 1 plus 1 is 2. The next row I start with a 1 and then I add. 1 plus 2 is 3. 2 plus 1 is 3, and then put one more 1 at the end. Next row, put a 1 at the end. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then put a 1 at the end, and so on. But when you use this method, it's exactly the same thing. So if you wanted to put a grid on it, you could say this is my downward motion of 3. This is my rightward motion of 3, and I end up with 20. And by the way, you're counting the number of moves. But the numbers also here are sort of like grid points as far as your intersections of roads. Let's do a second example in this image. There's a little bit more work to this one because we're going from A to D. That's a long way. Let's set up Pascal's triangle and maybe try to figure out what we did that'll make sense of this. When we did the first one, there were a total of 6 moves, 3 down and 3 over. You'll notice that we went down in Pascal's triangle until we got to a row that had a 6 in it. This is the 6th row, if you will, but you'll notice there's actually 7 rows. Sometimes we call this one the 0th row of the triangle. Let's see if we can use a similar strategy for this problem. It looks like there's a total of 10 moves. There are 3 across and 10 downward. Or we could look at it as maybe A to D is the downward, and then this point, which is 7 more, is the rightward. Either way is fine. We just need to be efficient in what we do. Let's try to draw a Pascal's triangle with 10 rows. And really it's going to be 11 rows. Keep that in mind. Pascal's triangle always starts with a 1 and then 2 1s. And by the way, when you draw Pascal's triangle, there will always be an offset. You'll never have a number directly underneath another number in the very next row. There's always an offset. And remember, you start with a 1 at the beginning and the end, and then to get the next number, you'll add these 2. 1 plus 1 is 2. All right, start with a 1. 1 plus 2 is 3. 2 plus 1 is 3, and then end with a 1. And I'm going to keep this up until I get to 10. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and again end with a 1. I'll show one more example, and then we'll just skim through it until we get all 10 rows. Start with a 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and again end with a 1. Now we're going to continue this process until we get to a row that contains a 10 right here. And here you have it, Pascal's triangle with 10 rows. So now what we need to do is follow the actual map. You go over 3 and 7 down. So we're going to go 1, 2, 3 over, and then 1, 2, 3, 4, 5, 6, 7. To say that there are 120 routes in order to get from point A to point D. Quite a bit more. Here's a new example, or so it seems. Remember, whenever we talk about problem solving, there's this step that we call the look-back step, and this is what I want to highlight with what we're going to do right now. This seems like a brand new problem, but it's going to be different than what you think. We're looking at a family with 5 children. We want to know how many birth orders if they have 3 boys and 2 girls, or possibly 4 girls and 1 boy. The idea of the birth order is that I'm not really concerned of which order the children are born in, but which order they have boys and girls. So for example, 3 boys and 2 girls could be boy, girl, boy, girl, boy. We don't really care which of the boys came first, just simply the birth order was boy, girl, boy, girl, boy. Another one could be girl, girl, boy, boy, boy. So those are examples of birth orders here. Let's see if we can put out all of our possibilities and work from there. If a family has 1 child, you either have 1 boy or 1 girl. If a family has 2 children, they're either going to have 2 boys, a boy and a girl, or they could have a girl and a boy, and this notation will mean something in a moment, or they could have 2 girls. Those are all the different birth orders. Now what I'm interested in doing is putting a 1 here, a 2 here, and a 1 here, for reasons I'll explain in a moment. Algorithmically, even though that's kind of a big word, I'm more or less just working by, and I'll start with what I see above and add a girl to it, then I'll go to the next one, I'll add a boy when I go left and a girl when I go right. From here, if I had 2 boys, I could do 3 boys. There's only one way to have all 3 boys. Or I could do 2 boys, then a girl. Or I could do a boy, then a girl, then a boy. Or a girl, then a boy, then a boy. There's 3 ways to have 2 boys and 1 girl. Or from here I could say you have boy, girl, 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 boy, girl, or girl, girl, boy. 3 ways to have 2 girls and 1 boy, and then finally, there's 1 way to have all 3 girls. So now, if we think about it, there is something going on here. When I go to the right and I add a girl, or I go to the left and I add a boy, I'm creating more possibilities. And so what it boils down to is your possibilities. If you take this one that has 1 more girl and add a boy, or you take this one and add a girl, you end up with identical possibilities, and it helps you find them all. So I can simply add the 1 and the 2 to get the 3. Similarly, 1 boy I could then have a girl, or 1 girl I could then have a boy, and there's 2 possibilities. This is the triangle all over again. 1 possibility of 4 boys. Or you could say 1 plus 3 is 4 possibilities of 3 boys, 1 girl. 3 plus 3 is 6 possibilities of 2 boys and 2 girls. Or you could have 4 possibilities of 1 boy and 3 girls, or 1 possibility of having all 4 girls. And similarly, 1, 5, just adding, 10, 10, 5, and 1 would be your possibilities, and you can kind of work your way through. So this would be 5 boys. This would be 4 boys and 1 girl. This would be 3 boys and 2 girls, which, by the way, that is one of our questions. this would be 2 boys and 3 girls, and then you have 1 boy and 4 girls. That's another question we were asked about. Or you could have 5 girls. So because we did the triangle before, this ended up turning right back into it. Now here is an interesting example. I'm going to try to set this up so that you can think about it for a moment, and then I give you a little bit of information, and then maybe you can think about the other piece. So what we're looking at is a really unusual circumstance. You've got Adam that turns 10 tomorrow. He's currently 9 years old. Eve is already 10 years old because she had a birthday yesterday. First off, just make sure that's clear. Adam turns 10 tomorrow. Eve turned 10 yesterday. So it sounds like Eve is the older one because she just turned 10 and Adam hasn't turned 10 yet. However, Adam was born before Eve. Adam is the older one. How on earth could that be possible? It seems pretty counterintuitive, but believe it or not, this actually is possible. And so think about it for a minute, gather an idea or two, and then we'll talk about it in just a moment. So feel free to pause. Hopefully you've gotten some ideas out of this. Let's take a look at what we have. What really is going on here is there is a leap year going on. That's one thing you may have thought about. There is some sort of leap year going on, and that will help to establish the fact that those birthdays are 2 days apart. That'll fix one problem. The other one that you may have thought about is that where they were born is going to be important. And so dates can be relative to where you are when they occur. Now, if this gives you some ideas and you want to think about them for a second, feel free to pause this video for a moment. Alright, now let me just go ahead and tell you the solution. Today is February 29th on a leap year. That's the only way that this is possible. Now let's add a little bit to it. We need to figure out what their birthdays are, and it should be pretty straightforward. Adam's birthday is tomorrow, so Adam must have been born on March 1st. Now I'm going to deliberately leave this because I want to add a little bit more. I want to put a time and a place, so I'm going to leave it there. Similarly, Eve was born February 28th. Now I do want to point out, with it being 10 years past, this is not a leap year that they were born. So their birthdays were actually 1 day apart rather than 2. It's just that today is February 29th. Alright, now we have to think about time zones. As I mentioned, time zones are going to play a factor. Now Adam is older, so we need to think about how could we make this work. Adam was born first. So let's suppose that Adam was born March 1st at 1 a.m., meaning that somewhere else in the world, it was still February 28th. So he was born at 1 a.m., and let's just say he was born at 1 a.m. in South Carolina. Notice that would have a different time elsewhere. So let's use another state for our example. Let's use California. So this is going to be February 28th at California is 3 hours behind us, so it would be 10 p.m. in California. So then Eve was born February 28th. We'll just say she was born at 11 p.m., which makes Adam older, and she was born in California. Notice that is March 1st at 2 a.m. in South Carolina. And this solves the problem. Adam was born March 1st in South Carolina, but over in California, it was still February 28th. So Eve has a birthday before Adam's, even though Adam is older. And for the birthdays to be so far apart, it's because it's February 29th, and the birthdays are 2 days apart this particular year. Kind of crazy, but believe it or not, this makes sense. This is possible. If you came up with even some of this, you should be proud of it. These are interesting problems to think about, and stuff like this is just there to say, hey, can I really think critically about what's going on here? Let's look at another example. Nick and Marcia are driving from Santa Rosa, California to Los Angeles, 460 miles apart. Now, Nick and Marcia leave at 11 a.m. and they average 50 miles per hour. On the other hand, Mary and Dan leave at 1 p.m. in a sports car, and we want to know who is closer to Los Angeles when they meet for dinner in San Luis Obispo at 5 p.m. So who is closer to Los Angeles? That's what you need to figure out. There's a lot of math that you could try here, but let me point you a little bit in the right direction. Or maybe I'm misdirecting you, I don't know. Nick and Marcia left at 11. They left 2 hours before Mary and Dan. Now, Nick and Marcia were told how fast they went. Mary and Dan, we are not told how fast they went. We're simply told that they were in Dan's sports car. Okay, maybe if it's a sports car, it was driving a little bit faster. We're also told the distance from Santa Rosa to Los Angeles. So now we just have a strange question of who is closer? Feel free to pause and think about this one, and then I'll let you know what's really going on in this problem. So here's the truth. The fact of the matter is, there is a lot of excess information in this. A lot. I do not need to know how many miles it is. I do not need to know what time Nick and Marcia left. And I don't need to know how fast they went. I also don't need to know what time Mary and Dan left, and I don't need to know that they were in Dan's sports car. All I need to know is they are driving the same route, they're heading towards Los Angeles, and they meet for dinner in San Luis Obispo. That's actually the key. Meet for dinner in San Luis Obispo. That's the key. They met for dinner. When they meet for dinner at 5 p.m., they are in the same place. There is no who went how far, how long. They just meet for dinner at 5 p.m. one way or the other. We don't know how they did it. We don't know any speeds. We just know that they met for dinner at 5 p.m. So what is the solution to this? They are the same distance from Los Angeles because they are all in San Luis Obispo. That's it. There was so much extra information that it can be confusing. Sometimes it helps to just get used to processing and looking for key phrases that might just tell you all the other stuff that you knew wasn't important.